Test. Test. Can you hear me, people online? Can you hear me? Just type a yes. All right, thank you. Okay, good evening. Let's get started. Let's continue on the directional derivative, and then I think we could finish this topic today. All right, let's do a very quick review. So I spent almost maybe 40 minutes or 35 minutes explaining what directional derivative is in the last lecture. The computation wise is really very straightforward. Okay, so let's rewrite this definition down and we'll look at a few examples today. Okay. So we're using function of two variables to illustrate the directional derivative idea, but it can certainly be expanded to function of more than two variables. Okay, so consider we have a function of two variable f of x, y. Okay. Then the derivative of this function f at point p naught x naught in the direction of u hat. U hat is a unit vector. We use AB to represent this unit vector. So we're looking at the derivative of this function at this point in the direction given by u hat. So graphically, basically, you have a surface, and this is your P naught location. And this is maybe your U hat location, right? So basically, if you can create a plane in the direction of a U hat, then that plane will intersect the surface and give you a certain kind of curve. Then the directional derivative essentially referred to is the slope at that curve, okay, on that location. And notation wise, what we do is, right, so the direction is given by df over ds in the direction u hat at the p naught location and equal to the del f at the p naught location dot u hat. So this is the directional derivative that we have derived from the previous lecture. We also provided a very short brief proof for this formula at here. So this is called directional derivative. Okay, so the name sort of explained it already. You know, it's a derivative you obtained while you're going in certain direction. And this is very different from function of single variable. Okay. So if I say it using similar description like function single variables, I could also maybe just a comments here. So this df over ds, doesn't matter whether it's p naught or arbitrary location u hat. Okay, so this you can also call this is rate of a change. Rate of a change in function f with respect to a displacement. So the function f with respect to displacement s, okay, in the direction u hat. Okay, so you can also describe directional derivative this way. You give a displacement to go to the direction in the direction u hat. So you're right here, and you go in the direction by a certain amount of displacement s. And then you look at how much change in the function value f. Right? So sometimes call it how much altitude change in the function f. And that gives you this directional derivative, or it's a slope concept. Okay? If there's a fast rate of a change increase, then you have positive slope, a positive directional slope. Otherwise, you may get a negative directional slope. So let me ask you a simple question. What if the directional derivative is 0? What does that mean? See the notation? Yes, you have basically no change in altitude. So you're literally walking around on the same altitude, right? Yeah, good. So let's get back to this computation formula here. So we'll look at a couple examples. Now, alternatively, I need to give you an alternative formula for directional derivative, very much like very much like the definition for a single function variable here. So alternatively, this df, okay, ds in the direction of u hat can be written using the limit notation. So let's still using function two variables, okay? So limit, so where are we taking limit here? So f is a function, you have x at here, you have y at here. So now remember, you are moving in the direction given by u hat. So let's write it down here. Okay, so you're moving in the direction u hat. So the x value will be changed slightly because of the change in the direction you had. So how much change in the x direction? So you look at this u hat, the unit vector in the x component is a. Then I could basically, let's say a multiplied by a very small value h, okay, representing basically you have an a here, you multiply by a little bit of scale, and that's how much you're moving in the x direction. So basically this portion in here is a delta x value. And then the y, same thing. I can use y plus bh. So the bh, this one here is delta y. So you have a very small change in the y direction, y-axis direction. And then here you have a small change in the x-axis direction. So this is the change. And then minus the initial position or the regional position value f of xy divided by this h, then you let the h approach to 0. So this notation is basically an energy of the notation as your single variable function derivative definition. So this definition will give you the directional derivative. Okay. Now, if you change your x, y to a specific point, x naught, y naught, and then you get exactly the directional derivative at this p naught location. Okay. So often in time, as a matter of fact, if you recall, sometimes when you learn derivative, one of the approach to get the derivative is to use the definition, right? To use the definition to derive for the derivative. So you could derive the directional derivative also using this definition instead of this formula. So basically, both of these can be used to calculate directional derivative. Okay, but of course, this one is much more easier to use and much more easier to use and right than taking a limit. So let's take a look at an example, and we'll mostly will use this one here to calculate a directional derivative. Okay. Let's consider this function. So this is a function of two variable. I need to calculate directional derivative at 2, 0 location in the direction of v equal to 3i hat minus 4g hat. All right, so the question itself is not that difficult, but the only thing we need to be careful is when I use the formula for directional derivative, right, so df ds in certain direction at certain point that equal to the del f at that point dot u hat. Okay. So when we use this formula, it is the unit vector that we're using at here. Okay. So the unit vector is used to represent the direction. So in this particular question, it didn't give you the unit vector. It does give you the direction, but the direction is hiding behind this vector here. So the first step you need to do is to normalize it to give you the unit vector before you apply the formula. Okay. Of course, here's v. I probably should change this to v hat instead of u. Yeah. So what's v hat? So let's calculate a number of things we need to calculate. V hat, you just have to normalize it. The magnitude of v 9 plus 16, 25, so 5. So 1 over 5, 3 negative 4. So that's your v hat. And we also had to calculate the grading function del f, the grading vector. Okay. So at the p naught is 2, 0. So let's put this 2, 0 at here. So calculate the gradient vector first. Partial f, partial x, give you e to the power y. Partial x, partial x. So cosine give you negative sine. And inside there's xy here, so you get y times sine xy. Right, that's partial f, partial x. Partial x, partial f, partial y. And now you consider x as constant and y as a function of variable now. So x times e to the power y. Sine xy, partial x. So this we're talking to y here. So this give you x at here. And now you have this coordinate 2, 0. Okay, partial derivative. Okay, just keep a clear head. Which one is a constant? Which one is a variable? And then substitute x equal to 2, y equal to 0. So when you plug in 0 over here, so sine 0 is sine 0 times 0 is 0, e to the power y, e to the power 0, which is 1. X is 2, 2 times 1, so 1. And then the next one is 0. So 1, 2, right? So the gradient at the P naught location at the 2, 0 location, it's 1, 2. So then you can substitute the two vectors into the directional derivative formula. And so what do we have here? So 1 times 3/5 minus 8/5. So -5, -1. The directional derivative is a -1. So you have a negative value. So that basically means you have a decrease in the function of f if you go in that direction. Right, so that's just very straightforward of an application of the formula for directional derivative. Okay, so I want to show you one more example. As you can see, directional derivative calculation, even if you don't understand what this exactly means, everybody can get a gradient and then you dot the unit vector, right? So you get a gradient. So computation is very straightforward. This one here, I just want to give you a little bit connecting the dots at here. So I don't need you to calculate. I want you to look at it and then tell me. Right? So if I have a function, 2 variables, and then what will be the directional derivative in the direction of I hat? What would that be? Very good. Not yet. Now, what would that be? You don't have to calculate. You can think about it, right? So right now what's I hat direction? I hat is in which direction? Which axis direction? X-axis direction. So when we see in the direction of I hat or in the direction of X-axis direction, basically which variable is being kept as constant? When you're walking in the X-axis direction, what variable is not changing? You can draw an axis here. If this is X here, let's say you keep walking in the X-axis direction. Everywhere along this direction, what is not changing? Exactly, the Y is not changing. If Y is not changing, then, right now we're not talking about a single variable here. We're talking about a function of 2 variables here. So basically, you are moving in this direction, okay? And you have a surface on the top of here. Okay? So df over the directional derivative in the height direction should give you not 0, not 1. Exactly. Partial f, partial x. Okay. So the partial f, partial x is a special case of this directional derivative, right? So if you want to now, if you want to prove it, and then you can show that del f dot I hat is 1, 0, and you will get partial f, partial x. Okay. So similarly, if you're going to take the directional derivative in the negative x-axis direction, so then you get negative partial f, partial x. So that's a connection between this directional derivative and the partial derivative. Right? Partial derivative is basically just a special case of directional derivative. Okay, good. The last part of the directional derivatives, let's look at this, some of the properties of a directional derivative. Right? And the property directional derivative is also quite important because I'm not sure if you still remember, I have an unanswered question, as a matter of fact, when we learned this grading vector. Remember when we learned a grading vector, we stated a comment. We said, a grading vector basically is a vector, give you a direction that points to the greatest increase in the function f. And I have said that I'm not going to be able to provide you proof now, so you have to trust me for the statement. So this is the part I'll be able actually to verify, to make to prove that what I said there, the comment, is correct. Okay, so let's take a look at the properties of the directional derivative. df over ds, the directional derivative in certain direction u hat, equal del f dot u hat. So basically, you have a dot product between two vectors. Like del f is gradient, u hat is the direction of moving. Then I can apply the formula for the dot product, which is the magnitude of the gradient vector multiplied by the magnitude of unit vector, and then multiplied by cosine theta. And theta is the angle between del f and u hat. And absolute value of u hat, or the magnitude of u hat, that has to be what? What's the magnitude of u hat? 1, exactly, right? So then you have gradient vector magnitude multiplied by cosine theta. So the directional derivative, right, is simplified into the magnitude of del f times cosine theta. And before even I can proceed, so maybe I just want to relate to one of the things that we stated in the first lecture of the class of this term. When you have a vector dot a unit vector, what does that give it to you? Length of projection, exactly, right? So when you have vector dot the unit vector, you get the length of the projection, which is this one here. Okay, so this is basically the length of projection, right, of del f in u hat direction. So now you actually can have a third alternative to describe what directional derivative is. So if you know what's the directional derivative, you could say, okay, directional derivative basically is the length of projection, the gradient vector in the direction of u hat, or in the direction of changing. Okay. Same thing, right? Okay, so then what are the properties? So I'll summarize 3 properties that are here based on the expression. Okay. First of all, if theta equal to 0, so theta equal to 0 degree. So when theta equal to 0 degree, meaning the gradient vector and the u hat, they become along the same direction, right? So remember the gradient, okay? If you have a function already, so if you have a function given, then the gradient vector, you can't change anymore because, once you have the function and you calculate the gradient at a certain location, right, that's determined by the function. So that you can't change anymore. But what you could change is the u hat. U hat is a direction, the user. I can choose to go from here to that direction. I can choose from here to go the other direction, right? Yeah. And the different direction will give you a different directional derivative. So now the question here is, if I choose the u hat, or if I choose the direction of changing to be the same direction as the gradient vector, then what happened to the directional derivative? Right, so that's the question. Basically, if u hat now is the same direction as del f, so what do we get? Cosine 0 is theta 0, so then cosine cosine 0 is 1. So you get what? You get the magnitude of the greeting vector based on this formula here. So what do you think of this value, the value of the directional derivative? So you look at the formula here, you have the magnitude of the greeting vector multiplied by a cosine theta, a sinusoidal function. A sinusoidal function always varies between -1 and 1. So basically means the magnitude of the greeting vector must be the maximum or the minimum. The maximum value for the directional derivative, right? So when theta equal to 0, you have reached at the maximum value for the df over ds along the u hat direction. Okay, that's a very important observation. So important basically means directional derivative give you the rate of change of the function f in terms of a small change in the certain direction. And now the first property tells me if I go in the direction, the same direction as the greeting vector, okay, if I go in the greeting vector here, then my directional derivative reached the maximum value. Okay, maximum value means reach the maximum change, possible rate of a change for the function f, or I can climb the fastest, right? That's happening only when theta equal to 0 or when this. So sometimes, understand that this part is actually more important than just the theta equal to 0, because theta equal to 0 doesn't necessarily translate to anything. But if you can translate theta to 0 to know that that means u hat in the same direction del f, okay, so then you actually have better understanding of this. That's when theta equal to 0. So then when theta equal to pi, okay, so let's consider the other extreme. So when theta equal to pi, so that basically means u hat is in the opposite direction as del f. So del f this way, and the u hat is pointing this way. And then you substitute pi equal into the cosine theta, then you get df over ds in the u hat direction equal to negative the magnitude. Right? And this is the minimum. This is the minimum value for df over ds. Okay, so you want the minimum value, then you have to go in the opposite direction as your greeting vector. So what does minimum value means? Minimum value means you have the fastest rate of change a decrease. So if you climb mountain, you're not climbing it, you're actually descending, right, in a fastest fashion. So that's u hat in the opposite direction as del greeting vector. And the third case is when theta equal to pi over 2. So pi over 2 is 90 degrees. So basically, it means right now your u hat is perpendicular to the greeting vector del f. Okay, so you're here and you have a del f, and you choose to go in the direction that's perpendicular to the gradient vector, then what is the resulted value for the directional derivative? So you plug in 90° here, cosine 90 is 0, so you get a 0. So directional derivative is 0 when you change or when you move in the perpendicular direction to the gradient vector. And I have just asked a question. When directional derivative equal to 0, that means there is no change in altitude or in the function value f. So basically means, right, if you are somewhere in the mountain and you don't want to climb, you don't want to go down, you just want to go around the mountain. So what do you have to do? And somebody has to calculate the gradient, somebody had to calculate the direction that is perpendicular to the gradient vector and tells you constantly. Of course, the gradient vector changes every time when you move, but so I had to tell you constantly, you move this direction, but always perpendicular to the direction of the gradient vector. So that way, you'll be able to get a constant altitude hiking around the mountain. Okay, so of course, when u hat is perpendicular to del f, I want you to, right, so let's say this is a plane here. I want you to be careful. You should be aware that, guess what? There are always two directions, right? Perpendicular to this del f. Now you think about it, if you go around the mountain, you can go either this way or you can go that way, right? So that's u hat. There are always two directions perpendicular to del f. Okay, good. So the three properties here, let's go back to the first property. You look at the first property here. Okay, you look at the first property. The first property says u hat is in the same direction, you get the maximum value for the directional derivative, which is the direction of del f, and the directional derivative value is the magnitude of the gradient vector. So if you look at the first property, guess what? That's exactly the comments that we have made about the gradient vector. Right? The comments of the gradient vector is it points to the direction of greatest increase, and its magnitude represent the rate of a change. And you can see here the magnitude represents the rate of change. The direction represents the greatest increase. Okay. So coming back to the statement, essentially it's verified. Okay. So let's take a look at an example. Okay. This example will be an example verifying the three properties, applying the three property set here. Consider this given function. So this one, we have seen it many times already. This is a paraboloid. Then first question is, so find the direction of maximum rate of increase at 1, 1. And the second part is to find the direction of maximum decrease at the same location. Okay, third question. Find the direction or directions of 0 change, okay, in F at 1, 1. All right, so that basically it's the three properties. Okay. So let's see how that plays out for this specific example. So 1, 1, it'll be somewhere here. Okay. So let's apply the three properties. So for the first one, it wants to find the direction, the maximum rate of increase at 1, 1. So according to the property, we all know that that direction, right, should be the same as the del F, okay, at 1, 1. Okay, so you had to find the direction u hat in the same direction as del F. Well, I guess I need to calculate del F, okay, at 1, 1. Okay, I got the function x squared y squared, so that give you 2x 2y at 1, 1, which is 2, 2. And u hat needs to be in the same direction as del F. So obviously I need to normalize this del F to give me the u hat. So normalizing this give me 1 over root 2, 1, 1. So it's that simple. So basically, if you go in this direction at 1, 1, then you get maximum rate of change or increase for the function f. Second question is the direction to give you maximum decrease at 1, 1. So as we learned from the principle, what do you think that you had? You don't even have to calculate anymore. So you had needs to be, just put a negative in front of the results from part 1. So u hat is the opposite direction as the grading vector del F. Okay, so the first two fairly straightforward. Okay, it's a third one sometimes needs a little bit of calculation. So the third one asking for the direction or directions of a zero change in the function f at 1, 1. So according to the property, what do you want? You want to find a direction that u hat that is perpendicular to the del F, okay, at 1, 1. So I'll show you two different ways to do this. Okay, so the first way is the most analytical way to do this. So I don't know what the u hat yet. So let's define u hat as AB. But I do know now is that the AB factor, the u hat vector, needs to be perpendicular to del F. Then the AB dot the del F, okay, needs to equal to 0. Right. When two vectors are perpendicular, means the dot product is 0. So what's del F? We already calculated 2, 2. So that gave me 2A, 2B equal to 0. Okay, so where should I go from next? I got two variables, but I only have one equation. So if I want to solve for AB, I can't, right? I have to have another equation in order to solve for AB. So where would be the second equation? How could I? Yes. Unit vector, exactly. Right? Don't forget, this is a univector. Univector means its magnitude needs to be 1. So basically, you get a squared, b squared, plus together and then square root equal to 1. And of course, this is equivalent to 2a plus 2b equal to 0, and then a squared plus b squared equal to 1. Okay. So unfortunately, this is not a set of linear equations. You got a one linear, one nonlinear, but a substitution still works. And so you basically, the first one you can even simplify this. The first one basically can be simplified to just a plus b equal to 0, right? A 2, you can get rid of it. So you can use substitution. Let a, now it's first one, a equal to negative b. Then you substitute into the second equation. So you get negative b squared plus b squared equal to 1. So that you get 2b squared equal to 1. So then what do I get for b? B equal to positive negative 1 over root 2. So that means when b is 1 over root 2, a is negative root 1 over root 2. When b is negative 1 over root 2, and a is positive 1 over root 2. So altogether, you get 2 directions. The first direction is, let's put negative 1 over 2, positive 1 over root 2. The second direction, positive, negative. Right, that exactly what remember what we said, when you're looking for vectors, when looking for a direction perpendicular to another vector, you have 2 directions. Okay. So now you got 2 directions. And the 2 directions are opposite to each other. Right? You can see they are just a sign difference. And they're both univector. And if you apply the dot product, you get a 0. So that will be the answer. Okay, good. So this is the analytical approach to solve for the U hat direction. Okay, so now alternatively, I want to show you one more approach. I mean, this approach may not work well for some of you. It does require you a little bit observation, but this should be a very simple observation. So we observe this 2a plus 2b equal to 0, okay? Or a plus b equal to 0. Okay. So a plus b equal to 0 basically means, you know, the a and b are literally opposite to each other, right? So what you could do is you can do a trial and error. You can say, okay, how about let a equal to 1, and then b must be negative 1. You don't want a 1, you want to use a 2, that's fine. You know, any number is fine. Okay. So you can get a equal to 1, b equal to negative 1. So this is because this is a very simple relationship. But once you get a equal to 1, b equal to negative 1, but you bear in mind, right? You know, this is not necessarily the actual value for AB. This is just your observation of value for AB based on a plus b equal to 0. The actual value for AB refer to a univector. So what you really have to do is you normalize this vector here, and you get exactly the same vector as this. And once you get this vector, then you can add another sign in front of it, positive, negative, and you get the same results as you calculated analytically. Okay. So that's called observation. Right? So if it especially works if you have a simple relationship presented over here. Observe it, will give you a 0, and then normalize it, and you get the same results as this one. Okay. Any questions? Yes. So we have A equal to 1, B equal to -1 here, right? And this is not a unit vector. So I normalize it by its magnitude, and we get √2 over here. Yeah. So, you know, if you have a different relationship, and I know sometimes that's 3A plus B may not work as well as A plus B equal to 0, but still it should work, right? As long as you do it correctly. Okay. Okay, so that's all about directional derivative. So the expectation for directional derivative is that it's not too much about the computation, because you're going to be able to get the formula sheets in your final exam. It's about more of an understanding of what's the meaning of a directional derivative. What's the connection between directional derivative and the grading vector? Okay. Now in assignments, I have I'll offer the link. And so this link directs you to this website here. And they have a fairly good of animation here. You can play with this directional derivative and the gradings on this website. Okay, so they just had a arbitrary mounting of surface plotted, and there's a point at here. The green color represents the direction, basically U hat. Okay. So you at this location, you can move around, right, to any directions you want. And then the bottom here give you the calculated directional derivative at different direction given by the green color vector. So obviously if you watch, it's a little bit small number here. When you move around, basically the theta value, you observe the directional derivative value. You can see at a certain value, you reach a maximum number. Okay, you reach maximum number. So that most probably this way, because when you walk this way here, it climb up the fastest, right? And if you go to the opposite direction, and most probably you're gonna climb down, going down the fastest. Okay. And then the next graph shows you both of the grading vector, the red one, and the directional derivative plus the U hat vector. So when you move around here, so you can see there's one direction, certainly the green one will in line with the red one, meaning the U hat is in the same direction as the grading vector. And then you look at this, the bottom here is a little bit small. It's that directional derivative value, and you get the maximum, okay? And obviously, it's climbing up the hill. And if you purposely make the direction to be perpendicular to the direction of grading vector, okay? And if you do it well, okay, it's not quite perpendicular. It's a little hard, yeah, well, right here. You see that directional derivative right now is 0. So this is a contour plot. So that clearly says you're gonna go around, right, the mountain along this contour plot. Okay. So this is a really good tool. You can, you know, visualize this relationship between the grading vector and the directional derivative. Okay. So take a look at it. That should help you with understanding the concept. Okay. So I'm a little bit early. I think I'm going to stop here. I don't have time to continue to cover different another topic. So we'll cover that in the next lecture. So anyway, I'll stop here. Any questions? Feel free to come over. And it's Friday. Have a good weekend. Yeah.
In this part of when you're getting the U vector direction of the gradient, how'd you get from this to
yeah?
So taking the magnitude?
You divide it. You just divide this vector by its magnitude.
Okay.
The
And then
mag-
simplify.
yeah, so its magnitude is 2 root 2.
Hmm.
So when you divide it by 2 root 2, then the 2 cancel become 1 1, right? And then
Yeah,
1 over
those
2.
cancel.
Yes,
Thanks.
good.
So here,
Hmm.
all you've done is
Hmm.
just 1 over the magnitude?
Mhm.
That's it?
Yep.
Okay. So is that,
So here, first I calculated gradient vector, right? At
Yeah.
the location.
yeah,
And then I'm supposed to normalize this gradient vector, divide by its magnitude, which is 2 root 2.
yeah,
Then I get this unit vector. The unit vector is essentially, as I said, I need it to be the same as direction as del F. Does that make sense?
kind of?
Yeah, you see, let's ask the question differently, right? If I got this del F
Yeah,
and ask you, can you calculate the unit vector in that direction? What would you do? Basically, you divide this by its magnitude.
yeah, so then you get 2 over 2 root 2, so you got 1 over root 2
That's
and
right.
1 over root 2.
That's right.
Okay, so all you've done here is, instead of writing in here, you've done,
I take out the one
yeah, you
over.
just take
yes.
a common,
Yes,
okay.
yes.
That makes sense.
Yeah, yeah,
Okay.
yeah. Yeah,
Really related to this topic.
sure.
Do graphs exist in 3D that
Hmm.
have flat surfaces? Or is everything a curve? Like in higher math, does that exist?
Come again?
So like for example, on the plot that you were just showing,
Yeah, yeah.
there's not really a point where there's like a flat plane within the equation.
Hmm.
Is there a point in like higher level math where like you can have a graph in 3D that has a part that's flat without being completely flat? Do you understand what I'm trying to say?
Not quite. So let me just think about it.
So
Could
like,
you, yeah, have a flat?
so yeah, so in 2D, right,
Mm.
you can have a plane.
Mm.
So I'm wondering if in 3D
Mm.
equations exist where you could have both the curves,
Mm.
and so let's say that at this surface it's flat, or like we cut it off here,
Mm.
and for a portion, instead of it being slowly going to a point,
Mm.
It goes up
A
and flat.
plateaued.
A plateau, yeah.
Okay.
Does that exist?
Oh, yeah, of course.
Yeah.
Why
okay,
not? Right?
Yeah.
So basically, you climb up, over this whole area.
Is that just a restriction then on the graph?
Yeah, so that is a really good point. So just like a function of single variables, okay, for example, right?
Yeah.
You have a continuous curve.
Yeah.
And you can calculate its derivative, right?
Yeah.
Okay, so let's think about the case what you just said for function single variables. So if you have a curve and then boom,
Yeah.
plateau.
Yeah.
Guess what?
Oh yeah, you can just rotate
At this location, right?
that. Yeah.
Your derivative actually does not exist because derivative approach this side is this value.
Yeah.
Approach this side is 0.
Yeah. Yeah.
So basically it
Yeah.
means the derivative of that function is not continuous.
Oh, so you can't have a continuous equation and have a plateau.
Right. So then
Okay.
if you have a function 2 variables plateaued, right?
Yeah.
There's a similar basically analogy to that too. So your yeah. So you're basically in this class we don't deal with we said we deal with nice function,
Yeah.
right?
I know. I was just
Yeah.
thinking, and I mean, it kind of seemed like an easy question, but also
Yeah.
kind of seemed like I wasn't quite sure of the answer, so I thought,
That's good thinking.
good.
Yes, yes. The definite exists. Yes.
yeah, I thought it should exist, but also thought I've never seen it before.
Oh no, of course, yes. So there in reality, probably not, but in
Yeah.
mathematical, definitely yes.
So now this maybe is going too far. So like,
Mm.
do those kind of functions exist in nature? As in like, there's like I think
It
the
does.
way I understand, there's like man-made functions kind of, and then there's like
Yeah.
functions that you can find throughout nature that are represented in nature.
Oh
Do
yeah.
they in nature as well?
Oh, yeah, absolutely. For example, here, how would you describe this function? Let's say if this is a function f of x, how would you describe it? And you describe it using piecewise, right? Let's say this is 1, this is x. You said when x is less than 1, you got something. You get greater than 1, you got something. And same thing, when you have a function two variable, you can also piecewise.
Okay,
Yeah,
okay,
within certain range, X and Y, and you have the flat plane.
Yeah.
And outside certain range, you got maybe a paraboloid. Yeah,
okay, thank you.
you're welcome. Yeah, good thinking. Yeah.